So this is ELC111, and this discussion or presentation is an introduction to analog to digital conversion. And we typically abbreviate this as ADC, analog to digital conversion. Now, ADC is simply a means of quantifying some analog quantity. And as we continue on here, we'll see that with the ADC for our discussion, our purposes, our ADC means that we not only quantify an analog quantity, but we provide that quantification in a form that is acceptable by a digital system or a computer. So we can also say this is a mechanism of digitizing some analog quantity. Now let's just talk about the process of converting some analog quantity into a measurement, a digital quantity or a quantity itself. So let's think about an analog quantity such as mass. So we've got some object, some giant thing, some blob, and we want to determine the mass of this object. Now, the way we would do this, or one way we could do this, would be to place this object on one side of a balance beam, and let's make another plate. Oops, missed a little bit. And of course, this beam is going to balance on some point here. And then we would take some items with a known mass, such as some weights, and we're going to pick out for our weights that have a mass of 1 gram. Now we would take these 1 gram weights and place them on this side of the balance beam. And we place the first 1 gram weight on here, and note that the mass of the object is greater than the 1 gram weight, so the balance beam stays as shown. So we stack another 1 gram weight up here, and of course this mass is still greater than the mass of 2 grams, so we would put another 1 gram weight up here, and another, and another, and another, and we would keep stacking these 1 gram weights up until the balance beam drops on this side, knowing that the mass on the right is greater than the mass on the left. So let's see, how many weights have we put on here? 1, 2, 3, 4, 5, 6, 7. So we know now that the mass of this object is greater than 6 grams, and we also know that the mass of this object is less than or equal to 7 grams. So we're able to quantify or obtain a measurement of this analog quantity. Now, for the example I have used here, the resolution of our measurement system is equal to 1 gram. The resolution is simply the what we'll say the smallest increment that we can achieve. The smallest measurement. We can also say this is the least significant digit in our measured quantity. In other words, I can't tell whether this is any value except as shown that it's greater than 6 grams and it's less than or equal to 7 grams. Now, of course, if I could have some smaller weights where each one was 0.1 gram, then I could improve the resolution or reduce the resolution, improve the precision of my measurement by then being able to measure the mass of this object to the closest tenth of a gram. Now, let's see how this applies to the world of electronics. And we're going to look at a possible means of performing an analog to digital conversion with voltages. So I'm going to start with a voltage comparator. And a voltage comparator is, the schematic symbol is shown, and we have one input that's labeled minus, one input that's labeled plus. And this is similar to what we saw earlier with the schematic symbol of an amplifier. The difference is that the comparator doesn't amplify the difference between the input voltages. The comparator simply looks at the two input voltages and makes V out either be high or low. So with our comparator, if the positive input, the non-inverting input, is greater than the inverting input, then V out is going to be high, which would be a logic level of 1. And if the inverting input is greater than the non-inverting input, then of course the output is going to be low, which is a logic level of 0. Now, going into the inverting input, we're going to apply some input voltage. And the input voltage is the voltage that we're going to convert to a digital value. So right here, I'm going to have a circuit that I'm going to call a staircase generator. And the staircase generator is going to provide the non-inverting input to the voltage comparator. And from the staircase generator, I'm going to have a digital output and for this case, we're going to have a 4-bit digital output. There we go, 4 of them. And this digital output is going to go to our computer, or this could simply be our memory system. Excuse me. And the output is going to signal the computer to tell it when to capture and hold the output of the staircase generator. Now, when we look at this 4-bit output here, we're going to call these outputs D3, D2, D1, and D0, where D3 is the most significant bit, and D2, D1, and D0, and D0 is the least significant bit. Now, our staircase generator, what it's going to do is always start with a, we see this already, oh, let me get it down here. Our staircase generator is going to start with a count of 0, and we'll look at a graph here that shows us voltage in the vertical axis and time in the horizontal axis, or the x-axis. So our staircase generator starts by making a count of 0, 0, 0, 0. And this will output to the non-inverting input of the comparator a voltage that is 0 volts. Then the staircase generator will generate a voltage that is 0, 0, 0, 1. Now, let's just say, for example, that a digital value of 0, 0, 0, 1 will make a voltage that is 10 millivolts. So the staircase generator will output 10 millivolts for some period of time. Now you need to, let's see, this is 10, 20, 30, 40, 50. We need to pick a value for the input voltage. And for the input voltage, I'm going to pick 45 millivolts. So this is my value of Vn. Now, down here at the bottom, let's look at the output of the comparator, V out, and at this point in time, we can see that the inverting input, Vn, is greater than the non-inverting input, V out. So my digital output, or the output of the comparator, is going to be a low logic level. Now, the staircase generator here outputs 10 millivolts, and it still, we can see that the value of Vn is greater than the non-inverting input, the output of the staircase generator. So the output of the comparator will still be low. Now, after some period of time, the staircase generator will now output 20 millivolts. And of course, we can see that right here, the non-inverting input is greater than the inverting input, so the output of the comparator will still be low. The output, oh, I forgot to put my count down here. So now the count has gone to 0, 0, 1, 0. This is 1. This is, excuse me, this is 0. This is 1. This is 2. And now the output of the staircase generator goes up to 30 millivolts. And of course, the count for this would be 0, 0, 1, 1. And the inverting input is still greater than the non-inverting input. The output of the comparator will still be low. The staircase generator now increases its output to 40 millivolts. And the count will be, guess what? 4. And the inverting input is still greater than the non-inverting input. The output of the comparator will still be low. But now, look what happens. This is going to be so exciting. Now, the staircase generator increases to 50 millivolts. And the count, of course, will be 0, 1, 0, 1. But now at this point, notice that the non-inverting input is greater than the inverting input. So the output of the comparator at this point now goes from low to high. And this is our signal to the computer to input that digital number or digital value. So the number that's input to our computer, 0, 1, 0, 1, that will be stored in memory. That information can be later sent to the display unit. We can transmit it. We can do whatever we need to do with our computer system. So again, all we have done is, just like in the previous example, we've kept adding 1 gram weights, or in this case 10 millivolt weights, to one side of the balance beam. The comparator is the electronic circuit that compares the input voltage and the voltage generated by the staircase generator to determine when inequality is met. Now, for our system here, the resolution is 10 millivolts. Notice that when we went from 40 millivolts to 50 millivolts, that's when the output of the comparator changed. So all we know is that Vn is greater than 40 millivolts. And of course, we know that Vn is less than or equal to 50 millivolts. So with this system, the smallest unit that I can measure is 10 millivolts.